Okay, so uh, in the previous slide, we defined um, connected and disconnected sets. And I'll remind you that if X is a metric space, and E is a subset of X, uh, so sets A and B in X are called separated if A closure intersection B is empty and B closure intersection A is empty. Now a set E in X is connected if E is not equal to the union of two sets A and B, such that A and B are separated. And this is something that I forgot to mention in a previous lecture in the definition, so it's very important. So in addition, I require that A is not an empty set and B is not an empty set. Notice that if A and B were allowed to be empty, then every set E can be written as E union empty set, and then they all would be disconnected. Okay, so I forgot to mention that A and B should not be empty sets. And the first thing I want to do now is to talk about continuous functions again. So I'm going back to chapter 4 and this section of chapter 4 about continuous functions and connected sets. And the theorem here says that if X and Y are metric spaces, F is a continuous function from X to Y, and E in X is connected, then F of E is connected in Y. So this is the image of the set E in Y, and the image of a continuous function applied to a connected set gives you a connected set. So notice that we now have those four cases. If function f is continuous, the image of open set is not necessarily open. The image of closed set is not necessarily closed. The inverse image of open set is open. The inverse image of closed set is closed, and the image of a compact set is compact. So this is a play between images and inverse images. And this theorem is about images, not about inverse images. So let's try to prove it. And the proof, I think, is very easy, simply because the definition of the connected sets were done in such a way that the proof is easy. So the proof is by contradiction. Suppose that f of e is not connected. Well, that means that f of e can be written as, I don't know, A union B, where A and B are not empty, and A and B are separated. So A intersection with B is empty, and the closure of B intersection with A is empty. All right, so this is the way I'm writing it. And so now all I have to do is I have to say that let's look at it. E is certainly, so f of e is A union B, and what that means, let me see if Rudin does the same thing I'm doing. If not, I'll do it just my way. Uh, so he's saying that let's suppose that G now is equal to E intersected with F minus 1 of A. So this is an inverse image of this A, and I'm taking only those parts of the elements of X which are in E. This is what I'm doing. And likewise, H is equal to E intersected with F minus 1 of B. Okay. So what I claim is that in that case, G and H, G union H is of course equal to E. You should agree with that just from these two conditions. And they claim that G and H are separated. Well, let's see why it is so. The closure of G, right, this is equal to the closure of f minus 1 of A. So this is a closed set that contains f minus 1 of A, and therefore it is a subset of f minus 1 of A closure. Remember that A closure is the least possible set with this property. So f minus 1 of A closure, this is a closed set because f is a continuous function. Uh, f minus 1 of A closure is a closed set, and this is the least closed set that contains f minus 1 of A, and therefore it is a subset of this thing. So likewise, we conclude that f of g hat belongs to A hat, and so uh, f of h is equal to B for the same reason. The G closure intersected with H is empty, and for the same reason as it is here, G intersected with H closure is empty, and therefore we have a contradiction because we assumed that E was a connected set, and yet here I'm writing my E. Where am I writing my E? Uh, yeah, here. So G union H is E, and if this f of E was not connected, then E would not be connected, and we have a contradiction. Okay, so this is a very, very important theorem, and let me explain to you why it is so important, at least one of the reasons why it is so important. And the main reason here is something that you used to call it in calculus 1. You called it intermediate value theorem. So now we're dealing with functions f, which are continuous functions from R to R, or f is continuous function that maps, say, an interval AB closed or open or semi-open. I really don't care. As long as this is connected, this is being mapped into R. And so you have two values, f of A, and you have values f of B. And let's suppose, without loss of generality, that f of A is less than f of B. Now notice that the image of the set f of AB is connected. And using the criteria for connected sets for real numbers, we conclude that if, I don't know, U is a number somewhere between f of B and f of A, then U belongs to the image of f of AB. And what that means is that there exists a C somewhere between B and A, such that f of C is equal to U. This is precisely the intermediate value theorem, and now I want to say a few words about intermediate value theorem. So for a second, let me go back to the very, very beginning of a discussion. Yeah, so what does intermediate value theorem says? It says that if I have a continuous function, let's say that look like this, and this is A and this is B, so this value is f of A and this value is f of B, then I will take any value in between here. And so there will exist a point between A and B such that the function takes exactly that value. Now, remember how we discussed continuity, and this is kind of close to what we want. It says that if you have a continuous function, then it cannot go from one point to another without skipping the parts in between. That was at the very, very beginning. And so for quite a while, people believed, and we had this intuitive definition of continuous function, and it's a function that you can draw on a paper without taking the graph, you can draw on a paper without taking the pen off the paper. All right. So this is something very, very similar to what we feel about continuous functions. And for many years, people believed that this should be a definition of a continuous function. So this was their belief. So let's suppose that you take a function that satisfies this intermediate value theorem, then this should be a definition of a continuous function. Well, it should satisfy intermediate value theorem very carefully because I can have a function like this, right? And then it will go on like this. So, of course, it will take all intermediate values between A and B, but it will not be a continuous function because it jumps around and I cannot draw it without taking the pencil. So there was a better way of doing it, and what it says is that a function is continuous if for any interval AB whatsoever, no matter how small, the intermediate value theorem holds. Well, unfortunately, as mathematicians often do, there are counterexamples. There are functions which are obviously not continuous, and yet they satisfy this intermediate value theorem. Rudin actually gives an example that I will talk about in a second, but let me do his example a little bit my way. So what I'm doing is I'm taking a function like this. Let's suppose that this is 0 and this is 1, and my function will go like this. So if it comes closer and closer and closer to 0, it will jump up and down infinitely often. And so the function f of x is given by this graph if x is not equal to 0, if x is greater than 0, and let's say it is 0 if x is equal to 0. Well, this is obviously not a continuous function because the limit of this function f of x as x converges to 0 does not exist. Remember, this function jumps up and down infinitely often, and so the limit simply does not exist. On the other hand, it obviously satisfies this intermediate value theorem because if a and b are not, if a is not 0, then this is just a continuous function and it satisfies the intermediate value theorem. Now, if a is equal to 0, then the value of the function is 0, and for any b greater than 0, between 0 and b, it will take all possible values. So this is like my picture of this function. Rudin gives you exactly the same example, and I'm going to follow what Rudin says now. F of x is equal to sine 1 over x if x is not equal to 0, and it's equal to 0, or if x is greater than 0, and it's equal to 0 if x is equal to 0. Again, it's a little bit illegal because remember we're trying to define everything. Oops, it's out of focus again. So let me see if I can focus it. I think this is better, right? Okay, so if you think about it, it's a little bit illegal because we haven't defined sine of x yet. The function sine will be defined in chapter 8 of Rudin, believe it or not. I don't know why this thing goes out of focus so often. But what does this function look like? Well, if x gets closer and closer and closer to 0, then 1 over x gets very, very big. And that means that 1 over x, being continuous, of course, it takes all possible values. In particular, it will take values such as uh, pi over 2 plus pi k infinitely often, and it will take values 3 pi over 2 plus pi k, so infinitely often. And that means that this function sign in here will be 1, and in here it will be minus 1. And so the graph of this function, more or less, will look exactly like I showed you. And as it gets closer and closer to 0, these jumps will be infinite. These jumps will come up infinitely often, and this will not be a continuous function. So the definition of continuity that I gave you is the definition of continuity that people are using to these days, and everybody agreed upon this definition. Let me tell you that, in my opinion, this definition is not perfect yet, but we don't know any, or I don't know any better definition. So if you look at the function f of x equals to x times sine 1 over x, if x is greater than 0 and 0, if x is equal to 0, now this time the graph of this function will still jump infinitely often as it comes closer and closer to 0, but these jumps will get smaller and smaller and smaller, and so the limit of this function f of x as x converges to 0 will be equal to 0, and so this function is continuous at 0. Now, remember how I said that the normal definition of continuous function is the one that you can draw without taking the pen off the paper? Well, I'm kind of doing this thing here, and if I could draw this function, I could draw it without taking the pen off the paper. But the problem is that I cannot draw it, period, simply because I cannot, in finite amount of time, do this infinitely many jumps up and down. So it's not a perfect definition, but the definition of continuous function you have now, and you also have this fabulous theorem about continuous function, which is an intermediate value theorem. Now, why is this theorem so absolutely beautiful? Let me try to give you a few examples of something we can do using this theorem in mathematics that no other subject in the world can be done this way. So let me give you an equation. F of x equals to, I don't know, x to the power of 5 plus 17 x to the power of 4 plus 3x cubed minus 2x squared plus 9x minus 201. Okay. Uh, And I'll ask, does this equation have a solution, have a real solution? Does f of x equals to 0 have a real solution? Now, what I claim is that the answer is yes. Yes. Well, why is the answer yes? Well, think about it. What will happen to this function? So this is a function. I can't believe I cannot focus this thing very well. Okay. What will happen to this function if x gets very, very small? Say if x tends to negative infinity. If x is minus a trillion or something like this. Well, that this x to the power 5 will be a huge, huge negative number. And it will be so huge that all of those other numbers will not kill the negative sign. In other words, then f of x for sufficiently small x, meaning they are large but negative, will be less than 0. And if x is equal to, if x tends to plus infinity, so this will be a positive number and the whole thing will be positive. And that means that if x tends to infinity, f of x becomes positive. And since f is a continuous function, and we know that polynomial function is continuous, it follows that if it takes a negative value somewhere and a positive value somewhere else, then there exists a value x naught such that f of x naught is equal to 0. Okay, so this is an example of something that only mathematicians can do, because what I'm trying to say is I have no idea what this x naught is. I have no idea how to solve this equation. In fact, I do have an idea, and the idea is that there is a theorem of Galois that says that this equation is simply not solvable using arithmetic operations. However, what I do know is that the solution exists. What I mean by that is that, like, if you ask, are there people with 3 arms? Well, how would you answer that question? You would go and you will meet every person on the face of the earth. And if one of them has 3 arms, you will say, yes, there is a person with 3 arms. If none of them have 3 arms, you will say, no, I looked at everybody and none of them have 3 eyes. In other words, to show that there exists a person with 3 arms, I have to find that person. Well, in mathematics, we have this trick where we can show that something exists without having any idea whatsoever how to find it. Likewise, we can show that something doesn't exist without going through all possible cases. So this, I think, is the beauty of mathematics. Let me tell you one more application of this theorem, which is very, very important. Uh, Again, I'm trying to position it. So let's suppose that f of x is a continuous function that maps a closed interval AB into itself. So this time, I'm insisting on something else. I'm insisting that this interval is being mapped back into itself. So the graph of the function should be such that the values of f of x when x is between a and b do not come out of a and b itself. It maps the interval into itself. Then, and this is a big theorem, there exists a point x between a and b such that f of x equals to x. Incidentally, this is called the fixed point theorem, so let me give you a quick proof of it. I'm going to look at the function g of x equals to f of x minus x. So what happens to g of a? Well, g of a is equal to f of a minus a. Now remember that a is the least possible value of the function, because f maps ab into ab, which means that f of a is either equal to a, in which case this is true, or f of a must be greater. It must be somewhere between a and b, so it's greater than a. And the conclusion is that this value is positive. Likewise, if I look at g of b, which is equal to f of b minus b, so b is the greatest possible value that the function can have. So f of b must be less than b, and therefore this is negative, and the conclusion is, once again, that there exists a point x naught between a and b such that f of x naught is equal to x naught. Okay, so this is called the fixed point theorem. And just for your future courses or for your future mathematical endeavors, this theorem have a very, very, very uh, far-reaching generalizations. And usually in topology, this is one of the absolute spectacular, phenomenal accomplishment of the field of topology. There is something called fixed point theorems. Usually the name Bauer fixed point theorems is attached to it. And so it is true not only in real line, that fixed point theorem, but it is also true, say, on a plane. And the way it looks is that if you have a convex set on a plane, now convex means that for every 2 points inside this set, a straight line that connects these 2 points, or the interval of a straight line that connects these 2 points, here we go again, lies inside the set. And if I have a continuous function f that maps this set back into itself, okay, so the picture is not accurate, but I assume that this set and this set are exactly the same. So in that case, there exists an x in this set, okay, such that f of x is equal to x. In other words, once again, there is a fixed point. Let me try to explain it in some way. So let's take a bottle of water. Okay, and there is water in here. And what I'm going to do, well, imagine that this is a bottle. And what I'm going to do is I'm going to give this bottle of water to some wild monkey that will shake it any way it wants to. It will turn it over, it will turn it back on, it will make it crazy. But as a result, at the end, you will have the water in the same position. Now, of course, the particles of the water may have changed the position, but this will be a continuous function provided that the bottle is not broken. It will be a continuous function from this set into this set, and then therefore there will exist at least one particle of water which will be in exactly the same position as to where it started. Well, the same theorem is true not only for two-dimensional things, but for n-dimensional convex sets. A in Rn. If you have a continuous function that maps A into A, then there exists an x naught in A such that f of x naught equals to x naught. It's a brilliant, brilliant theorem. It has several generalizations to infinite dimensional spaces, although I don't want to go into all the details at the moment. But this is one way by which mathematicians can accomplish something incredible. It is often if you can reduce your equations that you're trying to solve to a fixed point problem, and if your function have this particular property, then the fixed point exists, and so people in differential equations and integral equation and another field of mathematics constantly using this theorem to prove the existence of the solution of the equation. So again, this will not be on a test, but it's a brilliant theorem, and intermediate value theorem is just the first case of that theorem. So please, please, please remember this theorem, and when you take topology, if it's taught in a course of topology, then you should love this theorem. Let me make a few more remarks before I leave you to your own endeavors, and that is the connected sets themselves are interesting, especially in topology. And if you study topologies, then in topology, very often they talk about that set E but I'm not thinking of it as a subset of a metric space X. I'm thinking of E itself being a metric space, or more general topological space. And in that case, E is connected. Remember, if E is a whole metric space, then we know that this metric space is open because every metric space is open. Then E is called connected if E is not equal to A union B, where A is not empty and B is not empty, and A and B are open. In other words, the set is called connected as a metric space if it cannot be written as a union of two open sets, yeah, such that intersection of A and B is empty. It cannot be written as a union of two non-empty open disjoint sets. So when we talk about open sets now, I'm not talking about open sets in X like I did in the main course, but I'm talking about open set in this particular metric space E, and this definition is actually equivalent to the definition with separated sets. It just, rather than dealing with relative topology of the set E, in this course, Rudin decided to deal with topology of E as being a subset of a metric space X, and this is probably better for analysis. So also in topology, if you study topology and if you get to it, there are many, many other type of connectedness. There is something called pathwise connected. And the pathwise connected sets, what that means is that if I have any 2 points, I can draw a continuous curve which connects those 2 points. So this is usually called a pathwise connected set. And again, in general, and I don't want to go into difficult examples in topology here, but in general, there are connected sets that are not pathwise connected. If the set is pathwise connected, it is connected. But if it is connected, it's not necessarily pathwise connected. There are something called simply connected sets. And I will leave it to your course of topology to explain you what it is, but somehow the way it works is it counts. So suppose this is a set with holes, then it is pathwise connected and connected, but it's not simply connected because you can have different parts, different way of connecting these things that are not equivalent to each other. Okay, I'm not going to define the equivalent set. I will leave it to your topology teachers, but I do want you to know that connected set, pathwise connected set, simply connected set, these are important notions in topology, and that this intermediate value theorem, which led to a fixed point theorem, is a very, very important notion in analysis, and hopefully when you go to further courses in analysis and topology, you will study those theorems and appreciate it to a full extent. All right, so I think this is the last lecture. I really don't have anything else to say. So next week and the week after, on Tuesdays and Thursdays, I will be available, or other days too, I will be available to answer your question. And finally, I looked it up. I want you to know that the final test is scheduled by the university, not by me, is scheduled on May 7th from 12:30 to 2:30. So you have plenty of time to prepare. You have plenty of time to ask questions. I will try to answer them in the written form that I did before for a few of you. I apologize if it's not the best possible way to answer the question, but it's the best possible way that I can do. So as I said before, normally after the final exam, I take my students drinking to a bar, but unfortunately, due to circumstances, I cannot do it. This is the first time I'm not doing it in 40 years of teaching. This is tragic. So I owe you one. And good luck preparing and good luck on the final test. Bye.